So light also has particle-like properties. This is counterintuitive if one is used to thinking about it like waves, but it behaves this way. So the photo, this was, there's a number of ways this was noticed, but the way it was finally figured out was something called the photoelectric effect. So if you have a clean metal surface and you irradiate with light, you get electrons to be ejected from the metal. The energy from the light is hitting the metal and giving electrons in the metal enough energy to jump off. So that makes sense. You put energy in, energy of the system changes, it could have some reaction. In this case, it's kicking off electrons. Great. But what people had a really hard time with was the pattern that you got. And so the frequency of the light used for radiation must be above some threshold value, which is different for every metal. If light was more like a wave, you should be getting a little bit of electrons coming off no matter what frequency you put in. So something was up with it. If more light was just pumping in more energy, you should get energy of electrons coming off proportional to that. So there was something weird going on. So what you'd actually get is, if you look at the frequency of the light you use and the number of electrons ejected, until light was at a certain frequency, no electrons would be ejected. And once you reach that frequency, then electrons would be ejected. Weaker light would eject fewer, but higher intensity light would eject more. But if you had high intensity light of an incorrect frequency, you wouldn't get anything off, no matter how much energy you were pumping in. You just weren't getting any, nothing was happening. So, so electrons, the conclusion is electrons only come off the metal when the photon frequency is high enough energy to excite the electrons. And so what was proposed is that energy is proportional to some constant times the frequency. Right? That's what we're observing. The question is what that constant was. And you can work out, looking at the kinetic energy of the electrons coming out, that it would be equal to 6.626 times 10 to the minus 4 joule seconds. That's joule times seconds, not joules per second, which is very small. So as energy goes up, energy is proportional to the frequency. And so electromagnetic energy is light, it is quantized. It comes in these packets that are proportional to the frequency of the photon. And what you'd see is that the kinetic energy of ejected electrons is going to be Planck's constant times nu minus some theta, when theta is some metal dependent threshold. And when they're equal is when you're getting the energy equal to. So this explanation, which I did not go into in nearly enough detail, this is what actually won Albert Einstein his Nobel Prize. He only won one Nobel Prize. He did not win for special relativity or general relativity or proving Brownian motion, all of which are things that he did. But this is the one that won him the Nobel Prize. So another weird thing in the behavior of waves versus particles. So if you have some particle beam aimed at a wall with a tiny slit and you let a little slit through, think of, for example, the experiments used to show that atoms were mostly empty space, done with throwing alpha particles, still microscopic particles, but particles at foil. You'd get most of them hitting the wall, and then a few going straight through, and they just go straight through. Whereas waves, you can show with the mathematics of waves, if you have a point source of waves, you have wave crests, you have a parallel waves moving along, and so you can imagine that you're looking from above, that those are just, you're looking at the slit is like the shore, and you're seeing the waves approaching the shore that are approaching the wall, parallel to the wall, that if you let a little slit open, it becomes sort of like a point source of the waves, and it spreads out in a circle. So this is called diffraction. And this is very different than what you'd get in a particle. Waves spread out, particles stay focused. The other thing that we see is that overlapping waves interfere with each other. So if you have waves that are in phase, that their troughs occur at the same time, they add together. So if you have two photons that are in phase, they're the same, then their amplitudes add together. They behave as a wave that's twice as big. So however, if they're out of phase, if you have the peak of one that corresponds to the trough of the other, they actually cancel out. If they're not, and you get complete destructive interference. You get the same as if there is no wave. If they're more common is that they're partly aligned, and you get partial destructive interference. The wave is not quite as big if they're not quite aligned. And you can see that here we've got in water two little poles vibrating the water, and you can see places where the waves, you know, where it's light, where the waves are amplifying each other, and others where they cancel out. And you see these little patterns that pop up. So whenever you put, you know, waves together, you get very complicated patterns of interference, and interference both constructive and destructive. It looks really complicated, but you really get it by just summing together the two individual waves. It's the linear combinations of these. So that's what we see. And so a classic experiment showing wave nature of light is you have a light source and you have two slits. And then the light can pass through either slit, and then it's diffracting from each of those slits. And you can look what happens at a wall. And various places on the wall, they're exactly equidistant, or they're, the distances between the two slits differs by a wavelength or half a wavelength. So if the distance between the two slits differs by a wavelength, then they constructively interfere. So here it's with equal, it says equal path lengths, or length 1 equals length 2 plus a wavelength. So they differ by one wavelength, then it's constructive. If they differ by half a wavelength, then they interfere with each other. So waves in phase make bright spots, waves out of phase make dark spots. So that's pretty straightforward. You can do this, you know, with the right setup, you can do this in a number of different ways. So that's the sort of thing that you see. So which is it? So is light, and so light sometimes behaves like particles, sometimes behave waves. Which is it? You know, why not both? It behaves, it's neither a wave or a particle. In different situations, it behaves as a wave, and in other situations, it behaves as a particle. And so this is called wave-particle duality. You have to think of them as an object that mathematically in some situations behaves one way, in some situations behaves the other. It's neither of them, it has features of both. And why, or exactly what situations, that's beyond this course. And so we'll deal with that on a case-by-case basis. You know, in the example of a light being absorbed as a surface, it's behaving, interacting with atoms, it's behaving as a particle. If it's just diffusing through space without interacting with anything, it's behaving like a wave. Okay, so that's the segment there where we set up some of the physics of waves. Next, we're going to be talking about interaction of waves with atoms.